All right, so we are happy to have Anirbit Mukherjee from Wharton. So, Himanshu Asnani was supposed to be the host of Anirbit. He actually works in an area that overlaps with Anirbit's main area of research a lot more than I do. I'm completely, my ignorance about machine learning can't be overestimated. But I'm very happy to have Anirbit here, and his main area of research is the mathematics of machine learning, and he's going to tell us more about it. Fine, Anirbit, you can go ahead.
Thanks a lot for the invite and for the setting up this whole thing during this pandemic. Hope people will like it. So I'm going to assume most people have not heard much about neural nets, but if the initial part looks very basic, please let me know, then I can fasten up. I'm going to assume most people have not heard about neural nets. So let me start by defining neural nets. So the most important mathematical component that goes into defining neural nets is what is called the activation function. So activation function that is mostly used in real life and which is widely successful in the real world, and what most of our theories often focus on is what is called the ReLU function. So this is the analog of the gates. The ReLU gate is essentially a Rn to Rn map, which coordinate-wise takes the max of 0, the corresponding coordinate. So this is the most fundamental structure of all neural nets, this ReLU function. And given this ReLU function, which is the Rn to Rn map, you define a class of functions, which is called the neural net. The neural net class of functions is defined by giving a set of k+1 affine transformations between different vector space dimensions whose vector spaces line up correctly. The output dimension of the A1 is the input dimension of A2, output dimension of A2 is the input dimension of A3, so that they can be concatenated together, the matrices. The affine transforms can be concatenated. So given a set of k+1 affine transforms A1 to AK+1, a neural net is essentially a map which first undergoes an affine transformation A1, then you do pointwise ReLU, then you do affine transformation A2, then you again do a ReLU, and you keep alternating this till k+1 times. And this would be called a depth k+1 neural net. So that notion of depth here, as far as I understand, is the same as circuit complexity, usual Boolean circuit complexity notion of depth, and this depth I think match up. But there might be a +1 difference. I think depth k+1 in this literature is probably depth k in that literature. But more or less the same idea for depth of a circuit. And it's alternation of affine transforms and ReLUs. So this class of functions is what we are mad about at this point. It's a billion-dollar industry now, this understanding this class of functions. So why is this class of functions a billion-dollar industry? That's essentially the mystery that we want to solve. So why is this interesting? Before that, let me give a simple example of a neural function to keep one example in mind. So what you see on the screen is a R2 to R map implemented by a depth 2 neural net with 4 gates. 4 gates are marked in blue, the 2 inputs are marked in green, the output is marked in red. It takes 2 inputs, x1 and x2. And if you follow the algebra through the weight on the circuits and do the computation by hand, you can convince yourself that this net you see on the screen is computing the maximum of 2 numbers, maximum of its 2 inputs, x1 and x2. And this kind of max computing neural nets are very important theoretical structure. We have usually used these functions to prove theorems of this type. One of the first theorems we proved was something like this, that every continuous piecewise linear function is that in n dimension is a log n depth neural net. So it's an if and only if maps, right? And one way is the easy part. To show that every neural net is a continuous piecewise linear function is the easy part. The hard part of this theorem is to show the converse, that every continuous piecewise linear function is a neural net of depth log n. So this kind of proofs, which classification theorem proofs, go hugely through the understanding the construction of max functions. And there are a lot of open questions about max function representation using neural nets. I'm not going into that direction of research today in this talk, but just to point out that max functions are pretty non-trivial. We don't know enough about their representation with neural nets already. There are hierarchy questions we can't solve at this point. So this is one example to keep in mind, the max of 2 numbers of one neural net to keep referring to in mind. Okay, so why are neural functions exciting? They're exciting for experiments like this. Every face you see on the screen is output of a neural net. So these are not photographs of any real human being. These are essentially outputs of a neural net whose input was a random vector from the Gaussian distribution. The weights of the neural net were set in such a way that if I sample a Gaussian vector at random and give that as an input to the neural net, output is a realistic human face. So this is what makes neural net interesting. To my mind, this is the most fascinating neural experiment out there. Some people would say the most fascinating experiments are chess, defeating the chess. But I would say defeating the chess was already happening with IBM Deep Blue. So that's like bettering something known at an unprecedented level. But this is something that has no precedence before. Then you can somehow find assignments of weights to neural nets such that their outputs are realistic human faces. And it's not just human face, high resolution human faces. You can do it with all sorts of things. You can do it. So how is the neural net able to understand essentially natural distribution of images? The one would frame the question in that way. And those are, I would say, the holy grails of the subject. To understand how is neural net able to approximate naturally occurring distributions, like human face distribution. So this is what gets me excited. Like I want to one day be able to explain. One day I want to give a talk where I say I have a theorem to explain why is this experiment working. We are nowhere close to that. So this is the ultimate goal of the subject, explain this experiment. So we are going to do much milder things, aim for much milder things than explaining such esoteric experiments. So let me set up the mathematical formalism of how the theorems are set up. So the theorems are set up in the language of what is called the risk function. If you have, let me introduce it slowly. What is a risk function? So given a distribution D, a finite set of samples S, landscape is and a loss function L, I will define the landscape of a neural net as expectation of L, which is the loss function, evaluated at y, comma n of x, where n is the neural net. N of x is the output of the neural net in at input x. Expectation over samples x, comma y coming from a distribution D. And this is what is called the risk function of a neural net. And the left-hand side is a risk function, which is called a true risk function because it's sampling over some continuous distribution. If it is uniform over a finite set, we call it the empirical distribution. It's an empirical loss function. And understanding the behavior of L and LS as capital N changes, the neural function is changing, is the bread and butter of neural nets. And this is, we hardly know how to do this. And so the first kind of questions we want to ask in this subject is, are there classes of neural nets N? So N is a class of neural nets. Are there classes of N corresponding distributions D and L such that in those classes for that L in that D, finding a low risk net, so finding a member of capital N such that the risk function is very low is easy. In the worst case, it can be shown to be NP hard. So all sorts of hardness barriers are already known, but that's somehow never matters in the real world. Real world is easy for reasons completely unclear. There are trivial algorithms which will find out these low risk nets, a pretty complicated ND and L. And we have no idea why this is so easy in real life, although everything is NP hard. And that's the mystery we want to solve. Find out cases where you can provably find low risk nets. Sort of the opposite end of the problem is to say, find out large classes of N corresponding distributions D and loss L such that risk of every member of N is low. So this is like, there are two ways to frame the question. Find NDL examples such that in them the search for the low risk is easy, what is called the training problem. And the other way to frame the question is find large classes of NDL such that every net in the classes has low risk. And this will be the second part of my talk essentially. And it's up to people's opinions whether 1A is a hard problem or 1B is a harder problem. Some people, I think opinions differ on which way of the problem is hard. I think both are equally hard at this point. I think 1A is slightly harder maybe, but I don't know. I would say both are equally hard problems. And why
just one quick question.
Yeah.
Prahlad. So when you mention classes, what do you mean? So I understand classes of distributions. You have a family of distributions and talk, but L, you are not referring to a specific loss function or?
So typically it is classes of N. So typically you frame the question as fix D, fix L. You fix the D, you fix the L, but mostly what you're doing is the class is N. So N is the set of all neural nets you are looking into. Typically the sets you work with is you fix the architecture first, and then you say the class of neural nets I'm working it are all possible neural functions obtainable from this architecture for various different weight assignments on the edges.
Okay.
That's typically the class of neural nets.
So when you mean class of N, so what is it? What's the class? You're fixing an architecture and you're varying the weight varying the sort of the weight functions on the. Is that what the class is?
Yes. That's typically the setup.
Okay, fair enough.
And why are this search so hard? Why is searching for the global minima in this risk function so difficult? Here is the reason. These functions look terrible. So what you see on the screen is actually a two-dimensional projection of an actual neural risk function. And you can see how horrible these functions look like. They have crevices, mountain peaks, valleys, everything going on in this. So how the hell do you ever come to the global minima of this function? what algorithm is going to find the global minima here. So this is what makes it challenging. But what makes it also sometimes tractable is this kind of a phenomena, that very little changes in the architecture can alter the shape of the landscape from something so rugged to something pretty smooth. So that's what makes the theory work often enough, that we are able to make these careful choices of architecture so that maybe there is some smoothing happening. Or what is often true is the algorithm sees a smoothened landscape, although the actual landscape is not smoothened, because the effective landscape seen by the algorithm is smoother than what it actually is. And this is the kind of stuff what makes the theory work when it does. But in the worst case, generally, you might be stuck in the left side picture, where the landscape is super complicated. The Himalayan forest out there, the Himalayas out there, find the global minima in the Himalayas. That's what is the problem generally. And so this is what makes the search problem so hard. So the second kind of questions we want to ask is what is called discovering the generative model. So I did not enforce any condition between the y and the x, the label and the domain in the initial way when I framed the risk function. But suppose there is a function that connects y and x. Suppose there is a f out there, so their y's are f of x. Now the question is, can you find an n which is a close approximant of the function f? So you're not only trying to do risk minimization, but you're trying to converge to that neural net, which is a very good approximate of the f that is generating the y. So this is called discovering the generative model by training. So we will show so one of the classic examples where this kind of things has been open for a long time is sparse coding. This sparse code, neural nets can do sparse coding is a conjecture that goes back in the 1980s to Olshassen and Feld sci papers. And I think we made one of the first cuts at this problem to say that, okay, there is a way to set up a neural net so that you can get very close to solving this conjecture. I can show you some of the theorems that we have been able to prove in that regard. So this is the second kind of question.
A question for you. Are these problems interesting in large dimensions, or even in small dimensions they're still interesting? You're finding such a
good question. So I would say, okay, there are two ways to think about it. Does the theory get easier for small dimensions versus hard dimensions? Probably not. But the theory looks pretty hard to write either way. But one might say that the more interesting regime is to say, what is the theoretically most difficult regime to write proofs in? That turns out to be the scenario when the number of input dimensions and the number of parameters in the neural net both are going to infinity, such that the ratio is constant. Think of looking at a class of neural nets where the number of parameters and the dimension both are going to infinity at a fixed ratio. One might say that is the most hardest regime for the results to remain non-trivial. So that's the issue. The high dimension limit is non-trivial.
So does this mean basically you're saying it's sort of a linear size network? Linear size, the number of inputs and the number of weight parameters, that ratio you said is a constant, right?
Yeah, so that's okay. That by constant, I mean like that is sort of the minimal scenario when things get hard to prove, but that's not the most realistic case. The realistic case is where the number of parameters is a polynomial in the input dimension.
No, I mean, but even in the linear size network, the problem is already hard.
Yes, even the linear is sort of the baseline where already things will get hard to keep the answers non-trivial.
So, Anirbit, just to get more clarity, suppose my y was in small dimensions, say 10, 15, 20 dimensions, vis-a-vis y is in 100,000 dimensions.
Yeah.
Is the problem not easy when it's in 10, 15, 20 dimensions?
No, I don't see y dimension makes anything. Most of the theories we write is y equal to 1. Y equal to 1 dimension, and that's already super non-trivial. There are issues about whether high dimension y versus low dimension y makes the conceptual structure of the neural net different. There's a lot of research that has happened recently about it. For example, if you make the width of the neural net super large, then it seems that there is a conceptual difference in the behavior of neural nets for vectorial output versus scalar outputs. But from the theory point of view, output dimension is hardly a feature that makes theory harder or weaker. Okay, thanks for the great questions. So output dimension can be just set to 1 in all theories out there and nothing changes. It's already super hard, half the problems. Okay, so the third question is what I would call is the depth hierarchy kind of problems, which is what we initially used to do when we started off in the field, which is theorems of this kind. So one of the example key theorems we had proven is of this type as it's on the screen. So here what we kind of prove is that if you give me a k high depth neural net, k high depth parameter, then I can construct a function representable by depth k high and width w, which is exactly representable by a neural net of depth k high plus 1, such that for every low depth net, the infimum of the L1 distance on the 0-1 interval of the low depth net from the high depth function is at least delta. And it continues to be delta even when the width of the low depth net scales as width of the high depth net to the power of ratio of depth. So you can make the k high to k low as large as you want, and you can get as large a small depth neural net against which you still have this delta barrier, delta approximation.
So
barrier.
I'm having a bit of difficulty parsing this thing, but okay. So basically, you are saying that there are things that a depth k plus 1 neural network can do, which cannot be done efficiently by a depth k neural network, right?
Cannot be approximated efficiently. So this is the delta is the approximation barrier. It cannot be approximated efficiently because the infimum over the entire space of low depth nets is at least delta.
No,
So
but you can show such results because in the case of Boolean threshold circuits, these are very hard questions. People have been like,
so this is approximation hardness is in neural nets we can show. We can show in neural nets approximation hardness of this kind. What is not, if you want to compare it to Boolean threshold, I would say the comparison is more like what is hard here is to get a lower bound size, lower bound, which is exponential in the input dimension, suppose. So this is, if you can see the low width lower bound here is exponential in the width of the higher net. But can you get a width lower bound which is exponential in the input dimension? That is probably the right way to compare against Boolean circuit complexity results, little that I understand of that world. And that is very hard to reproduce here. So width lower bound, which is super exponential in the width of the higher net, is what is attainable.
Sorry, what?
You were saying something? Hello? I got, the voice got lost. So what I was saying
Arkadev, we lost you. Were you saying something?
So let me just complete what I was saying. So what I was saying is that if you notice the width lower bound in this kind of theorems, it's exponential in the width of the higher net. So W to the power of k high by k low. One can ask, can you get a width lower bound which is exponential in the dimensions, not exponentials in the width of the higher net? That kind of problems are still open, pretty much open. So that's that might be the regime of asking where is the comparison between those theorems. So what is much?
Sorry, I think my end things had frozen. I couldn't hear your answer at all. So what is actually the width? Can you?
So W is the width of the higher net. So I am so the difficult.
What is how do you define width?
So width is defined as you saw the linear transformations, affine transforms in the defining of the neural net, right?
Right.
So width of a neural net is the largest. You might say the largest dimension of any affine transformation occurring in the neural net. So it's like layers of gates. What is the widest
largest
layer
number of? So it's certainly upper bounded by the largest number of nodes in a layer.
Yes, it is the max over the number of nodes of every layer, max over all layers.
Right. Okay.
That's the width of a neural net. So this is the kind of function approximation results that we can currently prove. We can get super exponential in the width hardness barriers here. What is but what one might say, what is much more interesting here to get is distributional hierarchy. Can you show that the distributions generated by the high depth nets are hard to approximate by output distributions of low depth nets in some norm in the space of distribution, like Wasserstein norm? So that is the Wasserstein norm distributions. There are distributions generatable by high depth nets, which are exponentially hard to approximate by distributions generatable by low depth nets. So when the low depth nets are given, Gaussian distributions is important. So distributional hierarchy, I would say, is a much more interesting problem to solve, which very little is known about that. So we have some preliminary results in that direction, but getting this kind of exponential lower bounds in even width is out of scope at this point. So that's the sort of the next frontier one day we want to get.
So what you're writing down is also a Wasserstein claim, right? Over the uniform distribution on 0.
Yeah, if you want to interpret it that way, but that's not the that's not the really what you do. If you want, when you want to do distribution hierarchy, you want to move it to Gaussians.
Okay, but I mean you can always like.
I can sell it if you want it. I can sell it as distribution hierarchy if you want. But that's not the most interesting thing to do. If you want to move it to Gaussian, things get very hard. That's what is really interesting. So that's what kind of the work is underway. So the fourth kind of questions, okay, sorry. What I was saying is that, so let me just give an example of what the generative model discovery theorems look like. So this is an example of a theorem of that type. What you see here is the usual sparse coding generative model. X star are high dimensional vectors with the non-zero supports are sampled from an interval in R plus. So every coordinate of the X star vector is supported on a finite interval, and it has a support of psi h to the power of p, where p is less than half. It has to be less than half for most theorems to work. There's some known barriers out there, p star equal to half, p equal to half. And A star is an incoherent dictionary, a dictionary or incoherent matrix. Then what we can show is that there exists a loss function. There exists a loss function which is a squared loss and a corresponding risk function, such that this super complicated risk function of a neural net of depth 2, because you are first transforming the input y by w, and then you're transforming a w transpose. So there are two affine transforms working here. So it's a depth 2 neural network, such that the squared loss in the space of depth 2 neural networks, if you look at the critical point of this risk function, then the critical point in the regime of high dimensions is at A star, which is the original dictionary. So this, I would say, the first evidence of why sparse coding is doable by neural networks. And after this work of ours came out in 2018, Chinmay Hegde's group in New York University built on top of our theorem, and they were essentially able to show that the analysis that we require to do this theorem can essentially be repackaged into a convergence for gradient descent. So they were able to get a gradient descent convergence to A star also for this problem. So there's been a significant solution. If you combine Chinmay Hegde's group at NYU and our result together, it more or less settles the famous Olshassen-Weld conjecture about neural nets can do sparse coding.
But this probably requires you to start close or something, right?
Could you repeat?
So the convergence of gradient descent is for starting from where? Like, what is the initial?
The initialization in Chinmay Hegde's result, I'm not entirely sure where the initialize. I think it's random initialization, if I'm not wrong, in Chinmay Hegde's proof. So that's a detailed insight in Chinmay Hegde's proof of how much, what does he assume? I think it's a random initialization, if I'm not wrong. I could be mistaken in remembering his result. So, but what is still, you're saying something?
Sorry, what is incoherence?
So incoherence is a mod of, incoherence of a matrix is the maximum over all pairs of columns of the mod of the inner product between pairs of columns. So if an orthogonal dictionary is most incoherent, where every column is orthogonal to every other column, how close you are to all columns being orthogonal. So incoherence of a matrix measures, in a sense, how close you are to the situation where all columns are orthogonal to each other. So you need some kind of incoherence assumption. If you have columns which are very much like scalar multiples of each other, you are dead. Proofs will stop working. So you need some kind of a lowness of the magnitude of the inner product between pairwise columns. That's what incoherence gives you. It's a very essential part of the proof, this kind of incoherence assumptions. So, but what is still open in this problem is we don't know how to get a stochastic algorithm to converge to A star. That is still open. But in real life, when you do this kind of training, the algorithms that are used to train sparse coding on neural networks are much more complicated than stochastic gradient descent. I will go into some of those algorithms later on in the talk, but proving sparse coding for real life algorithms is still way open. This calculation that takes to do this theorem is extremely complex. It's about 30 pages of algebra it takes to prove this theorem. So there's 30 pages of algebra it takes only for just gradient descent. Proving this for non-trivial algorithms is going to be like an exponential blow up in the calculation required. No one has dared. So those things are still open. Also, experimentally, it seems that the global dictionary is in fact the global minima. The original dictionary is in fact the global minima. It's far better than just being critical point. So this is still open. We have no way to prove that this is the global minima, except for some trivial case. You can assume the original dictionary is an orthogonal matrix. In special cases, you can prove global minima. But in general, for incoherent dictionary, we still don't know why it is actually the global minima, which is experimentally well supported. This kind of conjectures of sparse coding are still open. Okay, so now let me come to the bulk of what I'm going to talk about. I'm going to mainly talk about neural training in much more easier settings in a sense. So one of the first results we showed about neural training was in 2016. This result got a lot of public traction in some sense in the community. So which was essentially to show that there is no hardness barrier if you want to do exact global minima finding, allowing me time which is exponential in width and dimension. If you let me use time as exponential in both width and dimension, then I can actually find the global minima in time polynomial in the training data size. So one could have asked that is there a possible NP hardness conjecture in the training data size? For a fixed architecture, fixed input dimension, is it NP hard to find the global minima in training data time? Turns out, no, there is no such hardness. So this was an interesting result that we showed in 2016, that empirical risk minimization can be exactly done in polynomial in training data set for a fixed architecture. So in recent times, since December 2018 or last October 2018, another line of research that has caught the imagination of the field is to say that suppose we are not working at fixed width neural nets like here. In the first theorem above, in the first block, width is a fixed parameter. It's a constant. And everything depends on the width. The runtime depends on the width. Suppose you don't work at fixed width, but you let the width itself scale with the accuracy guarantees you want out of the training. So if you want f1 minus delta guarantees on the training, and you want to converge in log 1 over epsilon time, let the width itself scale with epsilon and delta. You are looking at gigantic neural nets, asymptotically large neural nets. The width is poly 1 over epsilon 1 over delta. If you work in the regime of poly 1 over epsilon 1 over delta size neural nets, then it turns out that you can actually get very fast convergence to the global minima, which is a pretty interesting mathematical observation. There's been a lot of debate about whether this is realistic or not. This is what is called the neural tangent kernel regime. So whether the neural tangent kernel regime of deep learning is a realistic deep learning or not has been hugely debated in the community. There are lots of experiments out there trying to say the evidence for and against exists. I more or less believe it is not the real deep learning. Realistic deep learning is not happening in this asymptotically large regime. There are various ways of arguing this. So my bet is that it's a beautiful mathematical observation, pretty non-trivial observation, but this is not how actual deep learning is happening. Actual deep learning is nowhere near this asymptotically large.
What is N here?
In where are you seeing N here? Oh, okay. This N is the input dimension of the neural net.
No, input. Okay.
Input dimension. So this is the
dimension and the input dimension.
Yeah,
but,
this is the original Blum-Rivest NP hardness barrier. That your runtime has to be exponential, and if you want to find the exact global minima, that is the Blum-Rivest 1989 or something. That's the result. So that exponentiality shows up here. So in 2018, this happened. Exponentially large neural nets can be this asymptotically large neural nets. You can get convergence in linear time. So this has caught the imagination of a lot of people. We also have some ideas of some things we do in this regime, but this is not. I don't think this is a realistic regime. It's a mathematically very interesting regime because you can suddenly say something about large neural nets, which is not easy to say. But then the largeness amount you require is unrealistically large. You have polynomial in sample size 1 over epsilon and 1 over delta. This is like. Typically, neural nets are working at its training data size is 50,000. If your training data size is 50,000, you're looking at neural nets whose size is 50,000 to the power of 10. The neural nets of the size 50,000 to the power of 10 gates is just not real. Like no one uses this kind of width. So beautiful maths, not real. So during the summer this year, there was a sequence of results from our group and from a group in UCLA. Then we showed a lot of different training results for a single gate. The single gate training with the data not being realizable in particular was open for a long time. So we have written a lot of results, and the UCLA group about showing single gate training can be done in many regimes than previously thought of. So this is exact opposite to asymptotically large nets. Okay, single gate training. I would say single gate training is still open. There are still problems with even single gate training which we don't understand. But that's a separate topic to look at. It's where the edge cases are where we don't understand. So I would say in conclusion, all provable training is open in almost all practical regimes of where things are of practical interest. So what are the 3 properties I want in a practical neural net training proof? I would say these are the 3 things I want. I want the net to be finitely large. Means the size of the net should be greater than 1 and a parameter, W, not asymptotically large, not 1. Second property I want is the data should be non-realizable. So that the labels are not generated by another neural net of the same architecture that I'm training on. And the third property of a realistic proof would be that algorithm should either be SGD or very close to being an SGD. It should have a structural similarity to SGD. So if your theorem satisfies all these 3 properties together, I would say, okay, you're working in what I would call the challenging trifecta of deep learning, where all these 3 things are together. And writing proofs in this intersection of 3 properties is the real challenge. So let me show some examples where we can do such a thing. So one of the class of nets where we can do such a thing is this class of neural nets. If you're familiar with how convolution neural nets are defined, this is this essentially generalizes the idea of convolution neural nets. So this class of neural nets is the average over the gates, where each gate is getting y as an input, and it's taking an inner product of the input y with AK transpose W. The AK is a matrix which is different at every gate. So A is indexed by the gate K. So you take AK transpose, multiply it to W, you get a weight vector, and you multiply that to Y. So there's a shared weight W across all the gates. This class of gates is a theoretician's favorite currently. A lot of theorems I can prove about this class of nets, which I cannot prove otherwise. And this goes back to the thing I was mentioning at the beginning. Choosing the net architecture for theory is very important. Otherwise, you might just land up in weird landscapes where things become hopeless. So this is what I call a single filter convolution, because the W is the filter, and there's a single filter shared across gates. This is if you really go back to convolution nets, how they are defined, you realize that the matrix AK generalizes the idea of what I call patch extractors in conv nets. In conv nets in real world, AKs are the special case would be when AKs are 0-1 matrices with every column and every row having a single 1, at most 1, 1. So if you reduce to that special case, this is the patch extractor of real life conv nets. And also you can convince yourself that this includes the single gate as a special case. You can just set W equal to 1 and AK to identity, you get a single ReLU gate as a special case. It's contained in it. So this is generalizes the single gate, generalizes conv nets, but still mathematically maps the sweet spot out there. And for this, one can prove this kind of theorems you want. But what is more interesting is the kind of algorithms for which this convergence is provable. So this is not gradient descent. We cannot prove gradient descent even here. Even here, gradient descent is not provable. But what we can do is something slightly modified gradient descent. A slightly modified gradient descent is to say the update vector GT, which is not the true gradient of the loss function, but it is a weighted average of the inputs. Every input xi weighted by the error. I take the average, the weighted average of the inputs, and then pass them through a linear transformation M. This M is special. I can choose an M in such a way that this iterative algorithm, which looks almost like a gradient descent, actually converges to the global minima of this non-smooth, non-convex optimization. And that's the kind of thing that gets us excited. So let me give the formal statement of the theorem. It's a pretty somewhat complicated to prove the theorem actually. It's not easy even in this setup. So well, we need some assumptions on the data. We need something called parity symmetry of the data. The data is mirror symmetric. Every xi also minus xi in the input. I need some kind of a non-degeneracy condition on the data. There's some products of matrices are positive definite. Then I define something called a theta min. Theta min is what is the minimum in the class of the interpolation error. So theta min is the best interpolation error I can get on this data in my class of neural nets. That's what I call theta min. And W min are the neural nets which are the optimal interpolants. Then what we can show is that for arbitrary initialization W1, this algorithm has this convergence as you would actually want. That if the optimal interpolant is exact, then in terms of it's unique. If there is an optimal interpolant, it's actually unique. There is a unique neural net which does that. And you can reach there in log 1 over epsilon time. You can get epsilon close to the global minima in log 1 over epsilon time, but it's called linear convergence. So linear convergence in a non-smooth, non-convex optimization problem is always surprising to my mind. Like this is the behavior of strongly convex smooth function.
So question for you. Can you give us some, you're saying it's non-smooth, non-convex function and you're still doing global optimization. Can you give us some sense of geometry about this? I mean, how are you able to reach this?
Yes, so that's a good question. I'll get to saying something about it a little later. Next slide.
Okay.
I'll get to it later. I would say we still don't have a complete answer why the magic happens, but I'll say something about it next slide.
Okay.
And if the optimal interpolant has error greater than 0, then we can still get somewhat close, which is order the optimal interpolant's error. So this is, I think this is what we call constant factor approximation. I'm not entirely sure of the terminology. But we cannot get still order epsilon close when the interpolation error is greater than 0. If the optimal interpolant is not exact, then we can get order theta min close to the optimal interpolant. So improving this order theta min to order epsilon is still an open problem. It's a very hard open problem for various reasons I can explain. It will, I think, be a big breakthrough if somebody can get order epsilon instead of theta min. Okay, so now the question, Professor Sandeep's question. So there is a whole history to this kind of Tron algorithm. There's a history to Tron algorithms. Like the first Tron algorithm, one can say it goes back to the perceptron algorithm of the 1970s, or what's somewhat called the Rosenblatt algorithm of 1970s. One can track back the history of perceptrons. So perceptrons have been modified many times. So in 2010, there was a Shyam Kakade paper, Shyam Kakade, Adam Kalai, Varun Kanade paper doing something called the GLMtron. GLMtron got modified to something called the Alphatron by Raghu Meka and Adam Clevans. Alphatron got modified to something called Sparsitron. Then there was something called the Convertron with Surbhi Goel and Raghu Meka and Adam Clevans. So this is the history to such Tron algorithms. Our Neurotron essentially generalizes all these various algorithms in one way. But what is here now exciting is this, that all these previous Trons can be thought of, particularly when they're working on a single gate, as doing gradient descent on a surrogate loss. So the actual loss is non-smooth, non-convex, but the Tron algorithm in the single gate case can be rewritten as gradient descent on a surrogate loss. And the surrogate loss turns out to be strongly convex and smooth. So if you can do this reinterpretation and you can convince yourself, you can make it look more plausible why a log 1 over epsilon convergence happens despite it being non-convex and non-smooth. Because you can get a surrogate loss picture if you reduce to the one gate case. But when you are working in the multi-gate case, which was my theorem here, where you have more than one gates, we still do not know a surrogate loss picture. So I would say we still don't have a complete answer, complete post-facto rationalization of the linear runtime. But there is a reason to believe by looking at the one gate case that maybe this can be reinterpreted as gradient descent on a surrogate loss, which is strongly convex. But finding this surrogate loss in the multi-gate case is still open. I mean, I have tried a lot of tricks that worked in the single gate to write down that loss such that I can go back and write this as a gradient descent. Is GT the gradient of some loss function? It's still unclear. Particularly, is there a strongly convex smooth loss function whose gradient is exactly GT, so that I can reinterpret my Neurotron back as a gradient descent and hence convince why I have a log 1 over epsilon time. This closing of the loop is still open, I would say. At least I haven't been able to figure out this reinterpretation. It's an interesting question. I think it's an important question to solve. If you can solve this, then I think it will tie the Neurotron back into what is called implicit regularization. So if you have heard of this term called implicit regularization that people keep saying in machine learning these days, I would say the Neurotron is a part of the family of implicit regularization results. And you're essentially saying that instead of using the loss function, I'm modifying it in such a way that I'm screwing the gradient descent on top of that. But that picture is not yet complete because I cannot still interpret the multi-gate case as GT. I think it's an important question to solve. So also there's the issue of the way I showed the algorithm is deterministic. You can ask, can I do the algorithm, make it stochastic and analyze it as a stochastic algorithm? Yes, you can. So there's a separate paper where we did this kind of an analysis. Interestingly, the stochastic algorithm can be interpreted slightly differently. It can be interpreted as a data poisoning learning despite data poisoning. And in the same time, somebody is, let's say, disrupting the true data. And you're still trying to learn the original risk despite the distortion. So if you can interpret the stochastic Neurotron in that way. So that's the kind of thing that is possible if you go to stochastic settings. Okay, so much about Trons. But we need to face some hard truths in life. Tron is not what's working in the real world. Tron is not what is used in real world. Tron is a beautiful mathematical tool. Real life neural nets are not being trained by Tron. They're using much more complicated algorithms, which are barely within our mathematical reach. And let me now get there. So this is the algorithm, which is very commonly used in the real world. It's called the RMS Probe, root mean square propagation. I think that's how it's fulfilled. For a long time, even RMS Probe didn't even have a paper reference to it. It was just folklore. And we have tested it enormously. It's an amazing miracle, RMS Probe algorithm. For at least for small depth neural nets, it's pretty much the best out there. If the depth gets higher, you have to do some modification. We have worked on that also, but I'm not going into that direction. Let's just focus on RMS Probe for today. The RMS Probe, what it does is it does an update using not the gradient, but a super nonlinear transformation on the gradient. And the nonlinear transformation is very complicated. It computes a weighted average of every gradient seen so far in the algorithm. It exponentially downweights the past, but it still weights through everything. No gradient is left out. It creates this nonlinear combination of previous gradients, puts them into this diagonal vector, puts them into the diagonal of a matrix, takes the inverse square root of it, and linear transforms the true gradient by the inverse square root of VT. The VT's diagonal is a exponentially weighted nonlinear combination of history of gradient. So this is what is called adaptive algorithm. The adaptive gradient algorithms are what is the bread and butter of deep learning. And proving algorithms, proving convergences for RMS Probe is a super challenging business. I believe we gave the first proofs of convergence of RMS Probe for non-convex functions. So let me talk of something what I call the fast convergence, which is what recent work of ours has been. So to get fast convergence, we need oracle assumptions. And I say that, and currently the oracle that I need is what I call alpha beta xi distributed oracles. So these oracles have three conditions satisfying together. Their expectation of the G is X, expectation of G square is upper bounded by some constant into X square, and expectation of mod G into root over G square plus xi, this complicated quantity expectation is upper bounded by alpha into mod xi. So there are three kinds of control on the expectation I need for something for random variable to be called alpha beta xi distributed random variable. So this is somewhat abstract, but let me give an explicit example of alpha beta xi distributions. Essentially, you can create normal distributions whose variance is min of the 1 comma the mod of the average. Or you can even get heavy tail distributions like Laplace, whose variance has this same structure. And you can convince yourself that these kind of distributions satisfy the alpha beta xi condition above. Also, you can do mixtures. You can create mixtures of Laplace of this type and mixtures of Gaussians of this type and see that they satisfy alpha beta xi conditions. So there are explicit examples of alpha beta xi distributed oracles. If the noise in the oracle is of this type, I will call the oracle alpha beta xi distributed oracle. And these oracles are special because once I assume that I have oracles of this type, what I can get is what is called sublinear convergence. As in, I can, in order 1 over epsilon square steps, I can get order epsilon close to the critical point of the function. While the only assumptions on the function is that it has bounded gradients and it is smooth. I'm not assuming convexity. That's the main point. It could potentially be a non-convex function. Only thing I'm assuming it is smooth and it has bounded gradients. The bounded gradient smooth functions, I can get sublinear time convergence to critical point using RMS Probe. Once I have the oracle, have the noise be slightly nice. Just give me a little bit nice noise. Don't give me weird noise. Then I can get into trouble. So to put this into perspective, why these things are important, I would say there are 4 properties that we want out of any deep learning proof when working with real algorithms. First property I want is that the algorithm be entirely unchanged from what is real life working. So you might be familiar with the software TensorFlow or PyTorch, the 2 standard deep learning software, the TensorFlow and PyTorch. You can open up the innards of the TensorFlow and PyTorch, go into the source code of TensorFlow and PyTorch, you will see this algorithm running inside it. And our algorithm in the proof is entirely unchanged from what is actually running in the software. This is why I always want to emphasize. Keeping the algorithm unchanged and actual software implementation, I think is important. If you try distorting that, you're distorting a lot. Second property I want in the proof is that oracle have unbounded noise. You should not be using bounded random variables. If you let me use bounded random variables, I can improve a lot of proofs. But that's a bit unrealistic to say I'm using bounded noise. So then you're disallowing even Gaussian noise. That's a bit weird if you want to disallow even Gaussian noise in the oracle. So I want unbounded random variables. We also want constant step size in the proofs. Variable step size proofs are easy to write, and they are not always that good in neural net. Neural nets often enough are actually get away with their constant step size. You want constant step size in the proof. Second, you want sublinear rate of convergence. So getting these 4 properties together for a deep learning proof is what I would say is the holy grail. And you want the whole game is about what is this minimal amount of assumptions you can make and still get all these 4 properties to hold together. So as far as I'm aware, no other theorem in literature could get all the 4 properties together before this proof of ours. In particular, the first 2 is very difficult to get together, where you want the algorithm unchanged and you want the random variable to be unbounded. You can actually do in between things. You can typically get one or the other if you allow more weird noise. But by this particular control on the noise, I can get all these 4 properties to hold together. And we still don't have an example for single neural net on which this algorithm converges. In real world are not bounded gradient functions, they're not smooth functions, which is still a part of the assumptions of this kind of proof. So getting convergence of this algorithm, RMS Probe, which is actually used in real world on any neural net, is way outside current mechanics we know of, or how to write such proofs. All sorts of non-convex optimization techniques that we know of. Currently, there's a beautiful book out there on non-convex optimization by Kong Fang, a friend of mine, in fact, Kong Fang. You can look up Kong Fang's book on non-convex optimization. I would say Kong Fang's book is pretty much the state of the art in the field at this point. He has a 300-page book on non-convex optimization by Kong Fang. work through the entire book, and I'm certain no technique in that book will help you. So it's like no standard technique is helping prove these theorems. So there's something deeply non-trivial about proving RMS Probe, in particular for neural nets. Okay, so now let me come to the last part of the talk, which is about Bayesian learning. So what is Bayesian learning and why it is, in my opinion, one of the finest techniques out there at this point, most promising techniques out there about neural net understanding. So I need a shift of notation slightly. Earlier, the A1s were representing affine transformations. From here on, A1s are not affine transformation, but just linear functions, linear transformations. No bias terms anymore. And I'm going to use the vector A to denote a concatenation of all the vectorized matrices together. So vector A is essentially in as many dimensions as are the number of trainable parameters in the neural net. Neural net, typically 100 million. So vector A is a 100 million dimensional vector. So everything is in terms of this 100 million dimensional vector A. I'm never going to work in the language of the matrices A1 to AD, but I'm going to always work in the language of A, which is one vector in 100 million dimensions. So just keep in mind that picture. It's like a single vector in 100 million dimensions. So what is a neural net training? In neural net training, the parameters are changing. If the parameters are changing, essentially it's a 100 million dimensional vector, which is moving through some trajectory in the 100 million dimensional space. So every theorem we are going to write is in language of that vector in 100 million dimensions, which is having its own dynamics. But how does it change? It turns out the way this vector changes in 100 million dimensions is very, very systematic. And that's what gets us excited. So this is an example of what happens. It seems it always dilates. It's almost never contracts. This is the typical behavior. You start with a B. Mod B is the norm at the start of the training. Mod A is the norm at the end of the training. For various depths from 2 to 16, I have shown you the plot. It always dilates by a factor of about 2 to 3. Why? We don't know. We have no idea why this movement is always dilation and never contraction. It's a 100 million dimensional vector of weights is always expanding. And this is a very uniform behavior across neural nets, across training data. It's very hard to find an exception to this behavior. Why is it always dilation and not contraction? Second is how much angle does this vector deflect in 100 million dimensions? This shows that the deflection angle is pretty stable across depths. From depths 2 to 16, we have done these studies over various data sets, various architectures. The angle of deflection is almost entirely determined by the data set and not by the neural net. So the neural net, you could change it quite a bit, and you can see that the peak of the density estimate shifts very little, I would say, from depth 2 to 16. And it always decreases. When you increase the depth, the angle of deflection decreases, and the value of deflection is pretty stable to architecture changes. It's almost entirely determined by the data set. You can change the data set and change the angle of deflection by enormous amount. Enormous amount you can change. So the data set entirely seems to characterize the angle of deflection. So this makes us think that, okay, there are some stable geometric properties of this vector and how it evolves. So can you use that to get better results of risk bounds? So we need some rethinking about how you think of risk bounds. So what is a stochastic algorithm? Stochastic algorithm essentially is a way to induce a distribution on the space of neural functions by using the training data. The any stochastic algorithm is equivalent to a training data dependent distribution of the neural function space. So that means the natural measure of success of training should be expected risk, not the risk alone. Where you're taking another expectation on top of the expectation, where you say expectation over sampling the neural net from this distribution in the space of neural nets. And thus you get to the idea of expectedness. So if you want to measure performances by stochastic algorithms, the natural quantitative measure is expected risk, expectation being taken in this distribution of the function space induced by the training algorithm using the training data. And this makes it, motivates why Bayesian viewpoint is important. Because these distributions on their own are intractable. We cannot give an explicit functional form of these distributions on the neural net space. But Bayesian's framework gives the interest controllable middle ground. Says, okay, let me say I can set the distribution on my own. Can I set the distribution of the function space on my own in a way so that the expected risk is low? And that's what Bayesian analysis is able to get. So the way we do it is using a setup which was initially started in 2017 by Benam Neshapu, Srinath Bhojanapalli, and Nati Sabro in TTIC. They essentially started this notation, this formalism. We sort of keep to their formalism for it's a very nice set of notations they have used. The loss function on which these proofs work currently is what is called a gamma margin loss. The gamma margin loss is essentially the classification loss, but it's a gamma hard. So you would say that I'm classifying correctly if the output of the neural net on the correct class is at least gamma larger than every other output. So it's a harder loss than just the classification loss. And we introduce this important idea here, what is called the stable distributions. I would say a mu WS is a stable distribution for a neural net FW if I sample the weights from the distribution mu WS, then the maximum perturbation that can happen to the outputs of the neural net over the training data S is a finite set in infinity norm, is below gamma by 4 with probability at least half. It's a very mild condition of stability, but it is a constraint nonetheless. That with at least probability half, my infinity norm perturbation of the output when the net weights are disturbed from mu WS is below gamma by 4. And this lets us write the risk bound in a particularly nice form, which says that if mu WS is the stable distribution for the neural net FW, then there exists corresponding to mu W a distribution mu tilde, such that the expected risk in the mu tilde distribution is upper bounded by the KL divergence between the noise stable distribution, between the stable distribution mu W and the prior P. And this is like a prior P is chosen before you take the probability. So it's like for all prior P, there is an upper bound which is a KL divergence between the stable distribution and prior. Why is this interesting? Because it means that if I can guess the mu WS correctly before the training happens, so suppose before the training happens, you can make a good guess of the noise distribution to which the trained net would be stable. That means a P guessed before the training is very close to mu WS, then this scale divergence term is very low. And if this term is low, your entire right-hand side is low. And you can probably get a very good upper bound on the expected risk in the mu W tilde distribution. And the breakthrough result came in 2017 when a series of experiments from University of Toronto by Carolina Zugaiti and Dan Roy showed that you can essentially take a cluster of GPUs and run a search using cluster of GPUs in the space of distribution. They essentially ran a search in the space of distributions using cluster of GPUs running for days, essentially. And they showed these distributions exist. They were computationally able to show that there exists prior P such that this right-hand side is less than 1. The first time ever anyone got and you can see that this bounded loss function is bounded by 1. So this expectation is always bounded by 1. So your non-trivial upper bound has to be below 1. But theoretical prediction for this upper bound is in 10 million. The number on the left-hand side is always less than 1. All theory gives you numbers in 10 millions. So there's always a vacuous upper bound. So they were able to show for the first time ever that you can get non-vacuous upper bounds, that where the upper bound is less than 1, provided you use a cluster of GPUs to run a search on a supercomputer for days to find the correct distribution P. This I would say fueled theory for me. Okay, here is the experimental evidence that these P's exist, where this upper bound is less than 1. Can you establish it theoretically? So once this paper came out, I just went knocking in Dan Roy's door. I called up Dan Roy and I went to Toronto and I stayed in Toronto for 3 months working with him on trying to build this theory. And we came up with some nice P's. So there's a much more longer story to show how the P's look like, but I'm going to just summarize it in a diagram, not going to the details, innards of how these P's are constructed. Essentially what he says is that instead of thinking in terms of one net training, think in terms of ensembles. Think in terms of multiple nets being trained together. So blue is the vector in 100 million dimensions at the beginning of the training, the vector of weights blue. During training, the blue vector evolves the black vector FA. But while the blue vector is evolving to the black vector during training, I'm going to simultaneously train a cluster of red vectors, which are within a theta conical angle of the blue vector, and train them together and get this purple cluster of trained nets. So while the blue trains to red, blue trains to black, I also train the reds to the purples. And using this auxiliary cluster of nets, which has been trained simultaneously on the same architecture with the same training data, I'm going to construct distributions using these points. Essentially, I'm going to construct a mixture of distributions centered at these auxiliary nets, which I have trained alongside on the same training data on the same algorithm. And by using this kind of cluster argument, one can show that the risk bound of FA, which is the trained net, which is what I'm after the risk bound on FA, can be shown to scale with the distance between the purple cluster and the red cluster. And the distance between the purple cluster and the red cluster is always much smaller than the distance between the blue vector and the red-black vector, because this sort of is sensitive to the average case behavior. On an average, the clusters shift very little. There's some point in the red cluster which will almost always turn out to be very close to some point in the purple cluster. So the distance between the two red clusters, the red cluster and the purple cluster, is way smaller than the distance between the blue vector and the red-black vector. Typical theory scales with the distance between the blue and the black, which is much larger. But by using the cluster, I can write the theory in such a way that I scale with the distance between the purple cluster and the red cluster. And by doing this shift, I get way lower risk bounds. I can go into the details of how low we get and in consistency of this data. We have shown consistency of this data, like you can change a lot of things and still it is stable and all that. I'm not getting into those experimental details of how do you prove that the theory is very stable. But I want to emphasize one theoretical point, which I believe is the main mathematical point being made here. It is this about noise resilience. Neural nets are noise resilient. Well-trained neural nets can be perturbed by injection of noise, which is order 1 variance. And they seem to change very little. And we do not understand where this stability of neural functions come from. And essential heart of the proof of Pagbian analysis lies in proving theorems of this kind, which shows that if you have a neural net FA and I have a cluster of neural nets FAI, such that FAI cluster is somewhat close to FA in terms of outputs on a fixed training set S, then I can use this auxiliary cluster FAI to construct a mixture of distribution centered at the AIs with a certain amount of sigma, with each of them as a variance, which is a complicated function of the neural net, such that if I sample neural nets from this mixture of Gaussians, then with high probability, the largest distortion I will get with respect to the central net FA is very small. So there is so there are families of distributions out there, mixtures of Gaussians, which can be constructed corresponding to any neural net, such that sampling from this mixture of Gaussian does not perturb the function too much on the training data. But so I believe and I claim that this kind of theorem is sort of at the heart of a lot of things in deep learning. And if you can improve this kind of theorems, it will have a downstream effect of improving a lot of other theorems. And I believe this is some hard problem in functional analysis as to why do this kind of stable distributions exist for neural nets. If you do this experimentally, you will see that the sigma that I'm getting here, the upper bound on sigma that I'm using, is way underestimated. Like the actual sigmas in experiment for which this kind of stability guarantee holds is orders of magnitude larger than what we can theoretically prove. So we just do not know yet where this stability comes from. Neural nets are way more stable than theory can tell you. This is what the theory can currently tell you. And these sigmas are pretty small compared to what is actually real. So where will the improvement come from is in my mind an important question to think about. How can you jack up the sigma by a huge amount and still get this theorem to hold? So I have a guess. I have a lot of guesses about what can be done to make these theorems improve. I can go into this if someone is interested. But this is, I believe, is the mathematical core of this field at this point. Understanding noise resilience. Okay, so let me end by telling you some of the next steps here. What we are currently working on. I'll get to it little. Okay, not okay, let me get there. So as I said, the Neurotron is, I think, an important direction of agnostic learning with multiple gates. I think it's important to try to understand Neurotron's guarantees better. Can you show that Neurotron is in fact a full-fledged agnostic learner? As in show that given any epsilon greater than 0, Neurotron will always converge epsilon close to the optimal interpolant. This theorem is still not known. What we have is a constant factor, but not order epsilon. So then you can say that, okay, Neurotron is a full-fledged agnostic learner. This is still not clear. Proving any kind of convergence on neural nets with width greater than 1 is quite challenging, still not known, unless I tie the data down to Gaussian. So Neurotron sort of breaks this barrier in a way by making assumptions on the neural net structure. But if you say, I don't want to make the structure, just use the simplest neural net, 2 ReLU gates. I have a sum of 2 ReLU gates. That's enough to break all known theory at this point. We do not know how to do training on sum of 2 ReLU nets, which the weights have no relationship between them. So the 2 vectors are being trained independently. That's already enough to break all theory. No theory works for sum of 2 ReLU gates. So that's how hard the result theory is currently to write. And now let me come to what I think is one of the most important questions here. As I was emphasizing in the Pagbachian part of my talk, how that vector of weights changes in 100 million dimensions is important. So we believe the path in the 100 million dimensions through which the neural net evolves during training is very special. These are not arbitrary paths. It's not like you can randomly choose weird paths and get the training. It's not going to happen. So we need to understand what is special about this paths through which the net is moving. So it's a dynamical system, and it's a stochastic dynamical system. And we don't know what the paths are. Like, what is so special about these paths? And I think understanding these paths is a key step towards understanding deep learning. These curves are special. What curves are these? So let me end the talk by giving a conjecture, which is a much mega conjecture of where this path, what kind of paths these are. Let me introduce this idea of what is called elasticity. So if you're in physics, if you're a physicist, you're familiar with the idea of elasticity. So let me define something called the elasticity of a function. So given a neural net f and a loss function L, I'm continuing with the same notation. I define something called the elasticity function. So elasticity function is a function of two inputs, x and x prime. And it computes a certain combination of inner products of the predictor and the loss function in a particular combination. And this function is very interesting for many reasons that we currently know of. If you are familiar with the idea of tangent kernels, neural tangent kernel theory, you will notice that the first inner product inside the elasticity function is exactly the neural tangent kernel. But elasticity did not start off by trying to do what tangent kernels do. But it turns out that in continuous time, it can be related to the tangent kernel. It contains the tangent kernel inside. It sort of, in a sense, generalizes the idea of neural tangent kernels. And these elasticity functions are very interesting. And this is the conjecture that we currently have. That when neural nets train, they essentially undergo phases. That training happens in phases. The initial steps are very different from the middle steps. They're different from the later steps. Some people call the later steps as being the neural collapse phase. It's a terminology started by Donoghue at Stanford currently. He's calling it the neural collapse phase. But there are these phases out there. You think of phase transitions in physics. Essentially, these are like phase transitions in physics, I believe. The question is, what is an order parameter? Neural nets are undergoing phase transitions when they're training. What is an order parameter? So my claim is this elasticity function is like an order parameter. Just that I don't know where it diverges. It's not a divergence. That kind of analogy doesn't go through, but it essentially is. In the sense that if you look at the elasticity function at two inputs, which are very far away, x and x prime are very far away, then you can see that the elasticity function is always a decreasing function of time. During any training on any data, on any algorithm, this function is always decreasing with time. And how fast is it decreasing seems to label the phase of training you are in. So I can go into details of what these phases imply, but we have no mathematical tool at this point to prove the existence of these phases. Till now we think we have a tool, which is this elasticity function. Because we see that in experiments, this elasticity function decreases at very different rates at different times, particularly when the two inputs are far away. And this needs to be understood because this is a very consistent signature of the dynamics. And one might be reminded of things like, if you're familiar with quantum field theory, something called a two-point correlation function. The elasticity function here is behaving like a two-point correlation function. I think it has at some level, there's a analogy to how correlation functions behave, but we haven't been able to build a full analogy correctly, but I believe it is something like a correlation function, which is sort of tracking the phase behavior. And how it drops is a signature of which phase you are in. And this is mathematically completely intractable. Like if you work with even linear functions, where f is a linear function, proving that S elasticity is a decreasing function of time for even linear function is non-trivial. Try doing it, it's not easy. Okay, it's not like it requires a 10-page paper, but definitely requires a few pages of algebra to get this to show that this is a decreasing function for even linear functions. So proving this for neural functions is quite a way out. And to understand why is this capturing the phase behavior of neural nets, I think that analogy to phase transition is very strong. There's a lot of experimental evidence we have about it. And I think that's the direction we should move in. And one more thing I want to say about motivating this. The elasticity function does not start off as being a continuous time object, as I have defined it on the screen. It starts off as a discrete time object, actually. In a discrete time world, where we motivated is to say is this. Suppose when the parameters are at WT of the neural net, I try to make an alteration to the parameters WT such that I'm trying to improve the prediction at X. If I'm altering the parameters to make an improvement in the predictions at X, how much does it affect the predictions at a other point X prime? Relative to how much I've made an improvement in X. This relative change in improvement at two faraway points in the input space is what seems to be the key heart of deep learning. That there is this connection that when you make a change in the parameters to cause improvement at one point in the input space, it has an influence in how the predictions are changing at a faraway point in the input space. And this thing is what motivates the idea of elasticity. And experimentally, this seems to bear out that indeed it is tracking something very non-trivial about neural nets. It has a phase-like behavior, and we want to prove this phase-like behavior, which would essentially prove that there is something very special about this path, that there is a consistent provable property about this path, which is not, which is monotonic, but its rate of change is very highly dependent on which phase of training. So I invite all phase transition experts to put their brains into elasticity function of neural nets, which I think is an important idea going ahead. This is the end of the talk. And I just end with a picture of my various collaborators, Amitabh Basu, Pushpendra Rastogi, Akshay Rangamani. They're all various places now. He's at Amazon, he's at Johns Hopkins, he's at MIT currently, he's at Google, he's at JHU, all of these are JHU students. So this is the end of the talk. I hope you liked it, and please feel free to ask me any questions if you want.
Thank you. It was very passionate. Okay. So any questions, please? So I have one question about not the training thing, but about this sort of representability question. Okay. So I mean, when you say you can show this sort of depth K neural networks can represent a lot richer stuff than depth K minus 1 or whatever depth less than K.
So it's not clear it's richer. That's not clear yet. So we do not know that the function space changes with depth. That is not clear yet.
But there are functions which you can show can be efficiently.
Yeah. The efficiency change can be shown.
Right. So here, is this correct? My understanding that sort of, unlike in Boolean circuit complexity, you sort of look at a fixed n, right? The number of inputs. And then for that fixed n, you try to see how large a network do you need if the depth is shallower than if the depth is larger. Is that right? I mean,
yes, that's a yes, but ideally, but I would say the ideal theorems would be such that the width lower bound is, let's say, exponential in the input dimension. That would be the ideal kind of theorems to prove.
Right, but that's what we in complexity theory. That's what we have been trying to show in the, at least for Boolean functions.
Yes. So getting the width lower bound to be exponential in input dimension is a very hard challenge here, as is always, I think.
Okay. So those are still not known, right?
No, as far as I think there is okay, it is known in one case, which is for depth 3 versus 2, it is known. We know that there is a function in depth 3 which has an exponential in input dimension lower bound at depth 2. Depth 3 versus 2 is known. For higher depths, that kind of theorem is not known. But recently, there was a paper which somehow showed that if you can show some exponential in the input dimension gap at high depths, you can essentially break some other conjecture in complexity theory. There's some weird connection was recently made. So I'm not following that side of the literature at all. It was a paper by Ronald Eldon and Oha Shamir, who first showed an exponential in input dimension gap between depth 3 and depth 2. And then I think recently Oha Shamir wrote another paper showing that similar exponential in input dimension gaps for higher depths will be equivalent to some other famous conjecture in complexity theory. So there's something is happening there which I have not kept track of.
So this depth 3 versus depth 2, the depth 2 networks against which the lower bounds have been shown, are these depth 2 networks allowed to have large weights? The weight vectors, can they be large, let's say exponentially large in the...
Yes, I think so. I think that's it is allowed. It is allowed for the low depth weights to have large weights.
Oh, okay, that's interesting. So and these are not for Boolean functions, right? These are for...
No, these are real functions. So essentially, the main observation of these proofs go is I can give you some idea of how these proofs work in depth 3 versus depth 2. Essentially, it works on the main idea being, if you look at the depth 2 neural functions, what they are able to identify is that if you now Fourier transform them, in the Fourier space, depth 2 neural functions have a particular structure. They seem to have a Fourier spectrum which is supported on a union of straight lines. And this is where the main crux comes from. So whereas high depth neural functions, their Fourier spectrum does not have this weird support structure of being a union of lines. So when your Fourier spectrum is supported on a union of lines, that sort of can be leveraged into a proof. I think that is, in my way of thinking about it, that's sort of the crux of the proof. So you essentially want to create high frequency functions at depth 3 whose Fourier support does not look so degenerate, and that's how you sort of get the gap argument. So, but then you can ask, can I write a theorem about the support of the Fourier spectrum of a high depth neural net? That is very hard. We have tried a little bit on that front, but we have no idea if there's any uniform property about the Fourier spectrum. So that's what I think is the barrier out there.
Okay.
Is there a unifying property of the Fourier spectrum of high depth neural networks? That seems like the main question to my mind to answer.
Okay, thank you. Any other questions?
And these are very difficult to define Fourier spectrums for, because these are not even they're not differentiable functions. So you have to do lot of tricks to define Fourier spectrums. So this is like what is called a Schwartz function. You have to work in the Schwartz space, and it gets very tricky to get all these things to work. It's a very tricky business to get this kind of depth hierarchy results. But increasingly, it's not clear.
Why is differentiability important for Fourier?
Well, a lot of theorems are not easy to write unless you have the Fourier differentiability there. Like, how do you, like, for example, how do you define, what do I say?
You can define it for non-different. I mean, you can define it for a triangle plane.
Yeah, but then that requires some work, right? Doesn't come for free, if I'm not wrong.
Sorry?
At the output of these networks, you don't have a thresholding function, do you? Like a Boolean?
No. Real valued functions.
Real valued.
Yeah. Everything is real valued. If you make it Boolean sort of things, we have written a paper on Boolean neural nets also, but it's not that interesting a topic if you make it Boolean, because people say this is a very unrealistic regime you're working in. One might say.
Yeah, but on the other hand, in complexity theory, those are very interesting models, and there we cannot even show separation between depth 2 and depth 3. So depth 2, we don't have any lower bounds. So some of the problem becomes possibly more tractable by not having a hard threshold, at least in the depth, from what you're saying. I don't know.
It's not clear to me. It's not entirely clear to me that you're going to get there are some kind of theorems that are easier to prove if you go to make the neural nets Boolean, like we have been able to get. But
what do you mean by Boolean neural nets? Is it same as a TC circuit or something else?
By Boolean neural net, I mean both kinds of situations. When the input is Boolean and the input is Boolean and the output is free, or you can say I have an input is Boolean and the output is still real.
But what are the gates to it?
Gates are still real. The same everything is less.
Yes, I think that's what I think what Akadev is asking.
So the gates ReLU. So so I think the gates being ReLU in the middle does not change much. If you only care about polynomial size, there are results that will show that if you have a hard thresholding function, then ReLU gates, hard thresholding function at the final output gate, then I think the ReLU gates and Boolean threshold gates or any sort of interesting activation functions would compute the same class of Boolean functions.
But the lower bounds do not hold. So for example, lower bounds of Boolean circuit complexity get tremendously weakened when you make the thresholds with ReLU. For example, I can give an immediate example. Immediate example is the Kane, the Rand-Williams Daniel Kane result of superlinear lower bounds on depth to LTF functions. So
I'm talking about I know that result. So I am talking about super polynomial.
That does not hold. That is not known to hold for ReLU if you replace the threshold with ReLU.
Sure, but the point is, if you care about low these things, that's true. But I'm just saying, ReLU circuits can be simulated by threshold circuits and vice versa with polynomial blowups, low polynomial blow up, maybe quadratic or so. So we have a paper about.
No, I think there's an exponential blow up there.
No.
There is an exponential blow up, if I'm not wrong.
I'm assuming a hard threshold and no weights, no limit on the weights or on the.
Yeah, the weights I think will be important then. Yeah, so that's the.
I think if you have a ReLU circuit and you want to.
No, but a ReLU circuit at the very output. This I want to emphasize at the last output gate there I have a thresholding one.
Okay. That probably is making a lot of difference. Then that is probably making a lot of difference. Yeah. Otherwise, there is an exponential blow up if I'm not wrong.
Yeah.
I mean, for example, these kind of things are not known. If you take an AND or tree in Boolean circuit, people keep talking about this AND or trees. If you take a depth 3 AND or tree.
No, but you need to have a thresholding at the top, right? If you are trying to say, if you want to make your ReLU circuits compute a Boolean function, otherwise it's going to be.
But I can do the other way. I can say I want to set the weights in such a way that the output is Boolean when the input is Boolean.
Yeah, but that's too constraining.
So if I allow for that, then there is an exponential blow up.
Sure.
So if I take a depth 3 AND or tree, and you say I want to write the depth 2 neural net which computes the depth 3 AND or tree, then everything is exponential. We don't know how to get anything below exponential. So there's an exponential blow up when you try to compress a depth 3 AND or tree to a depth 2 neural net, and we have no way to reduce this exponential blow up currently. So LTF of LTF, if you want to simulate it by sum of ReLU, there is an exponential blow up, which we don't know how to get out of. So this kind of...
we can talk about that offline. Okay, I might have questions about those things. Okay, but we should end this now. Okay, so it was very nice having you. Any questions? One last time. Piyush, do you have one?
No.
Piyush, this is phase transition. This is your field. We have brought it close to your field now.
Okay.
So Arkadev, you can just end the meeting as usual, and the stream will be saved.
Okay.
I mean, anyway, it's there on YouTube. For people who want the link, I mean, this is the link. I'm just adding that on chat. Yeah.
Okay. So I can just end it, right?
Yeah, you can end it and it will. Yeah.
All right. Thanks, Anirbit.
Okay. See you.